Hello, and thank you for following this tutorial series on TRV analysis. If you go through this entire series, you will become a master in TRV analysis and you will be able to perform them for work. The first step of this series will be to understand what a TRV is. According to the IEEE definition, the recovery voltage is the voltage that appears across the terminal of the circuit breaker after interruption. This voltage may be considered in two successive time intervals, one during which a transient voltage exists, followed by a second during which a power frequency voltage alone exists. Before going to a concrete example, let's see the general case. When a circuit breaker is closed, the voltages at each terminal are the same and the voltage across the breaker, which is called the longitudinal voltage, is zero. Now, when the breaker opens, it separates the original circuit into two circuits which have different transient responses. The circuit breaker opening is a perturbation, and therefore each circuit will react to it. Because they have different transient responses, their voltages, V1 and V2, will be different, and therefore the voltage across the circuit breaker, which is equal to the difference between V1 and V2, will be different than zero. Let's go back to a more concrete case. Here, there is a fault on a branch, so the circuit breaker opens. As soon as the circuit breaker opens, two circuits are formed. V1A is the voltage on phase A on the source side, and V2A is the voltage on the other side. Here at the top, we see the longitudinal voltage across the breaker. This is the recovery voltage. And because we have actually zoomed on the transient part, it is the transient recovery voltage. If we zoom out, we can see the full recovery voltage, which eventually goes to steady state. During TRV analysis, the system voltage across the circuit breaker is called the prospective TRV. Okay, so far so good. So what is the big deal out of it? The deal is, can the breaker achieve the current interruption? When the breaker receives the opening order, the contacts separate, but the current is not interrupted right away. An arc is formed and the current keeps circulating. When the instantaneous value of the current approaches zero, the arc extinguishes and the circuit is open. We say that circuit breakers interrupt the currents at the zero crossing. Because of the arc instability around the zero crossing, a small current of few amperes can be shocked, which can create even more challenging TRVs. The shocking current magnitude depends on the type of circuit breaker, vacuum, SF6, etc., and the topology of the network around. When the arc extinguishes, the circuit breaker is still opening, and its poles are separated by a gap. The voltage withstand of this gap depends on the distance between the contacts. While the breaker is opening, the withstand voltage increases and reaches its maximum when the breaker is fully opened. It usually takes between 50 and 200 microseconds for the contacts to open completely. The longitudinal voltage withstand of the circuit breaker is called the inherent TRV. Although it is very hard to know precisely the withstand voltage of a circuit breaker gap, standards exist to classify circuit breakers. For a given voltage rating and current interruption capability, a voltage withstand envelope is provided. Circuit breaker manufacturers must ensure that their circuit breakers have a withstand capability equal or superior to the one provided by standards. This is why, for TRV analysis, we usually use standard inherent TRVs. We superimpose the prospective TRV of the circuit with the standard inherent TRV of the circuit breaker. One of the main constraints for a successful opening of the circuit breaker is that the prospective TRV remains inside the inherent TRV envelope. If it is not the case, there is the risk of a dielectric breakdown across the circuit breaker. If this happens before a quarter cycle following the opening, it is called a reignition. If this happens after a quarter cycle following the opening, it is called a restrike. In this example, we can see that the circuit breaker starts opening sometime before the current zero crossing. When the current is interrupted, the circuit breaker is almost completely open. This is a lucky case because the longitudinal voltage withstand of the circuit breaker is then maximum when the TRV appears. It is obvious that the most challenging opening will then be when the circuit breaker opens just before the current zero crossing. In this situation, the risk of reignition is maximum. This is why it is usually the scenario to consider when performing a TRV analysis, and this is the default option in EMTP. It exists devices named point-on-wave controllers which monitor the voltages and currents and operate the circuit breaker so the contacts are completely open at the current zero crossing. These solutions can theoretically reduce the risk of reignition, even though studies must be done considering the precision of the equipment and its risk of failure. When comparing the prospective and the inherent TRVs, there are two particular points of attention. The first one is the TRV just following the current interruption. At this moment, the rate of rise of the recovery voltage is a concern. The second one is when the TRV reaches its peak value. Most of the time, the circuit breaker will then be completely open, and we have to verify that the peak TRV is lower than the maximum withstand voltage of the circuit breaker. The engineering objectives during a TRV study is to make sure the circuit breaker will successfully open in any situation. In other words, it is to make sure the prospective TRV remains inside the inherent TRV. As we will see later on in this tutorial series, the analysis will be based on worst-case scenarios. One, giving the worst rate of rise of the recovery voltage. This will be by simulating a single-phase short-line fault. One, giving the worst TRV peak by simulating a three-phase terminal fault. In all cases, we will consider the circuit breaker opens right at the current zero crossing. Of course, there are many challenges around TRV analysis, and we are putting a lot of effort in training our technical support staff and adding many features in EMTP to make sure these studies are as easy as possible for our users. The first challenge is actually to interpret the standards. Because of the high complexity of the circuit breaker current interruption phenomenon, the standards addressing this issue contain a lot of information which are highly case dependent. The circuit breaker inherent TRV ends up depending on the circuit breaker class, its rated voltage, its interrupting capability, but also the type of fault to clear and its current magnitude. There is a big room for error. To solve this issue, we incorporated the IEC and IEEE standards in our circuit breaker model, which will automatically draw the correct envelope. The second challenge is to determine accurately the prospective TRV. Because of the high frequency content of the TRV, many EMT-type software will suffer from numerical instabilities, and engineers will not evaluate correctly the system TRV, sometimes without even knowing it. In EMTP, all the models, and especially the line and cable models, which are the most sensitive elements, are validated with our industrial partners toward measurement. And because sometimes parameters for such studies can be very hard to find, our technical support team is specifically trained to provide our user references for typical values. The prospective TRV also highly depends on the system. Each of the applications mentioned here requires special attention. We will see all that in the next videos of this series. Thank you for watching this video. If you have any questions, please ask them on our LinkedIn EMTP community. If you would like to get yourself informed of when we release new contents like this one, please subscribe to our YouTube channel or our newsletter. Have a good day. Bye.